Hello and welcome back to Hilbert Spaces, the video series where we talk about inner product spaces and operators on them. And in today's part 10, we will talk about the important concept of an orthonormal basis. Indeed, the projection theorem from the last video guarantees that every Hilbert space has such an orthonormal basis. Now, before we start explaining how this works, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you can download additional material for all the videos. With that said, let's immediately start by explaining the term orthonormal you might have already learned in linear algebra. For example, in Rn, we have the canonical unit vectors denoted by E1, E2 and so on. And if we have our standard inner product on Rn, then these canonical unit vectors satisfy two conditions. First, they are mutually orthogonal, which is the first part in the name here. And the second part just means that each vector has length 1. And there you might already know that both things can be put together if we use the Kronecker delta. So we can just write EI with EJ in the standard inner product, and then the result is just the Kronecker delta with the indices I and j. And this is quite a simple symbol because we either have 1 or 0. So if the indices are the same, we have the length of the vector given as 1, and if they are not the same, then we have the orthogonality. So this is what you should remember. Exactly this condition for vectors is what we call orthonormal. And now it's not a problem at all to generalize that to infinite dimensions as well. In fact, the notion of an orthonormal system makes sense in every inner product space. So for this definition, we don't need the completeness of a Hilbert space yet. And there we can just consider a collection of vectors, so a family of vectors, which we also call E with an index. However, in order to distinguish it from the finite dimensional case from before, we call the index alpha. So alpha goes through a whole index set we can call capital I, and this one can be an infinite set. So this is our whole family of vectors from our inner product space X. And now we call this collection of vectors an orthonormal system if it satisfies the same condition as before. This means E alpha together with E beta in the inner product gives us the Kronecker delta. So this is already the whole definition for an orthonormal system, and to keep it short, we just say ONS. And now a special case of an orthonormal system is a so-called orthonormal basis. And there please be careful, such an orthonormal basis is not a vector space basis as we know it from linear algebra. In fact, only in the finite dimensional case, it's an ordinary basis in that sense. However, it turns out that in the infinite dimensional case, such an orthonormal basis is a very good substitute for an ordinary vector space basis. And usually we just say ONB in that case. And the short definition just says an ONS is an ONB if it is total. And now this notion total is not complicated at all. It just means that all the linear combinations we can form with the ONS are a dense subset in X. And you already know this subset is what we usually call span. And please don't forget, a linear combination always means that we consider a finite sum. So dense in X means that the closure of this subset with respect to the induced norm is equal to X. This means no matter which X you choose in our vector space X, you can always approximate it with a linear combination. Or in other words, if you put an epsilon ball around this X, you always find infinitely many elements from this span. Hence we can choose the epsilon as small as we want. We always find a very good approximation for X in our span. So this is the term total, which is only helpful in an infinite dimensional vector space. This is clear because in a finite dimensional inner product space, we can always make this span equal to X. Okay, and now if you want, we can describe this denseness property here in a precise way. This means we put the picture on the right hand side into a formula. So for every vector x, we find a small epsilon ball around it and a linear combination consisting of vectors from our ONS. This means we can take n vectors from it and n scalars to scale them. So the scalars are called lambda1, lambda2 and so on and come from our field. And by using these, we can form a linear combination which is a finite sum of vectors. So there we would write that we have E with index alpha j. And there j goes from 1 to our capital N. Okay, so this is an element in our span and it should also lie inside our epsilon ball around x. This means x minus this linear combination has a length that is less than epsilon. So our norm induced by the inner product is less than epsilon. And there we have it. This is the property for the span, which we call total. So you should remember this definition. A total ONS is an ONB, which means that the linear combinations can be chosen as close as we want to any point in the vector space. So you immediately see this is different to an ordinary basis of a vector space, because there we would always find a linear combination such that we have equality. However, as we will see, this definition here for an ONB gives us a big advantage when we deal with Hilbert spaces. For example, we already know our small L2 space, which can be seen as a generalization of our Rn. Simply because the corresponding inner product looks like the standard inner product in Rn, just with an infinite series. Also, the canonical unit vectors we could define look almost the same as well. For example, E1 has zeros everywhere except for the first position. And then obviously we can continue this procedure with E2, E3 and so on. So in fact, here we have an ONS with infinitely many members. So it's easy to check that this property with the Kronecker delta is satisfied, so we have an orthonormal system. And now the natural question would be, is this also an ONB? So can we show this total property for the family as well? And in fact, this is not hard at all, because every vector x is an infinite sequence with entries in C. So every x in L2 can be written as a sequence x1, x2 and so on. And now these entries can be chosen as the coefficients for our linear combination. Hence this linear combination with our ONS gives us this same vector, but this one ends at a given index n. Or more precisely, we have an infinite sequence, but after xn we only have zeros. But now the important fact is that we can choose this capital N as large as we want. And this implies that the difference between x and this linear combination is a vector that has zeros at the beginning. And then the norm of this vector is what we have to calculate. And by definition, we know it's the square root of an infinite sum. Indeed, in the infinite sum, we have the absolute value of xj squared. However, now we know that we start with this index j at the value n plus 1. This is important because we know by the definition of our small L2 that this whole thing goes to 0 when we send n to infinity. This means by making n larger and larger, we can make this number as small as we want. In particular, we can make it smaller than a given epsilon. This is all we need to know because it implies that our span of the ONS is dense. So we get a nice example of a total ONS. And by definition, a total ONS is what we call an ONB. So our result here is that our infinite dimensional Hilbert space has a nice ONB. And indeed, we see that we only need countably many elements in our ONB. So we need infinitely many, but it's the smallest possible infinity we have. And we will see in the future that this happens for a lot of interesting Hilbert spaces we consider. And at this point you might ask the question if we can always extend a given ONS such that we get an ONB in the end. And I can already give you the answer, which is yes, but we need the completeness of the Hilbert space. And I would say this is something we should prove in the next video. So I really hope I meet you there and have a nice day. Bye bye.